Okay, or 10 missing. Never mind. Okay, we'll start. Okay, so today we'll be, hopefully we won't have trouble anymore. The color's back. Sound seems okay. Alright, so first of all, there's a lot of problems. First of all, I cannot find. Okay, first of all, we will have recitations. Wednesday 1 to 2. We will have that. Okay, we will have Wednesday 5 to 6. Okay, question: who cannot make for both Wednesday 1 to 2 and 5 to 6? Sorry? No. Okay, don't ask or squeeze in first. The question is, can you all fit in this 2 times now? Can everybody fit in this 2 times? You cannot fit in any time, right? What's wrong with your schedule? Even Thursday also, you have a lot of problems, right? Correct? Sorry? You got what, tutorial? No, 1 to 2 has no tutorial anymore. 1 to 2 has no tutorial. The DG has been cancelled already. Okay, so who else? You? Why? Say again? Hey, shh. What? No, don't tell me that. What's that? 1 to 2, what is it? Ask to switch out. The other one? Switch the tutorial. Yeah. Okay, what else? Who else has any problems? No, what's that? 5 o'clock? 5 to 6 is what? Lecture, is it? Lecture cannot switch, but tutorial can switch. I get this is quite switch you. Anybody else? Yes. Okay, who else has problems? Okay, no problems, very good. So we will fix these 2 times, 1 to 2 and 5 to 6. Who goes where, we'll figure out soon enough. I'm gonna die. Okay, then it's not the end. So, okay, I've already posted this online. Okay, so this is the current schedule. It's very small, but let's try. Okay, so this is the DG, the discussion group schedule. The 1 to 3 discussion group on Wednesday has been basically gotten rid of because unless Mr. Ryan wants to have a one-on-one with the TA, I think not. Very romantic, yeah. So we have gotten rid of it. So basically there are some new times here. Okay. Okay, we will pause again later to look at this, and then any problems come see me. Okay, we try our best. All right, those are no problems. Then it's no problems. Okay, but later on we will see again. So this year is a hazard. So we'll see how it goes. Okay, so these are the times. Okay. What we'll do, in fact, is that we'll create extra tutorial group at Wednesday 3 to 5. Okay, so there are a lot of people on Wednesday 3 to 5. The two groups. Then the rest will be those times. Later you will see, I'll put up online. In fact, it's online already. It's in the admin folder. You can see which tutorial group you've been assigned to. Again, there are problems. You talk to me. We'll try to move you around. Okay, so this is the way it is every year. This year is worse because this year I also have conflicts with the tutors. So I had a lot of trouble trying to fit the tutors into the DGs. But hopefully by next week we will actually sort this out. Okay, one problem is that the venues the venues are not all fixed yet. I need to fix that this afternoon. Okay, so we can only inform you next week exactly where the venues are, even if the times are okay. Okay, any questions? Okay, so by next week we should stabilize. All right, but it's always like that. All right, so good. So this is the tutorial scheduling and the recitations. Okay, so today's agenda. All right, so what we'll do is we'll cover some topics, and what we'll do is, number one, to go and tell you more about what's the difference between recursion and iteration. I'm certain that after Wednesday, some of you are still not too clear. Okay, so for recitation, I give homework, right? Which is to rewrite the, the add to order and whatever, right? In iterative form. Who can do it? Who cannot do it? or can do it? Cannot do. Okay, so cannot do, never mind. Cannot do, we'll look again. Okay, hopefully after today you have a better sense of what it is about. Next recitation we'll go through it again, I suspect. So again, the sort of stuff we throw at you, alright, and you requires effort on your part to kind of learn it. Okay? Alright, so first thing I want to talk about is this recursive process and iterative process. Okay, so the main difference here just is the following. If you take an operation, some kind of procedure, right, and then you essentially evaluate the procedure, apply a procedure or something, okay, you will expand out, right? So if the expansion does not involve this thing called deferred operations, then it is a iterative process. If there's this kinds of deferred operations, which means that you have all this like plus signs, whatever, then a lot of parentheses, and it opens up and it closes down, that is known as a recursive process. Alright, so iterative process typically are always the same shape, okay? And recursive process actually expands. Okay, let's take a look. Okay, so one thing is to understand how to do this, right? Because this is one of the things that we ask you to do. So how do you convert the recursive process to iterative process? Okay, we call the factorial, which is this, n factorial is this, okay? Now, obviously, you can just take the definition, write the code. Okay, so far all follow, from the definition up there, to write this code should be trivial, right? No brainer, right? It's almost a direct translation. Okay, anybody has any trouble? Okay, the top line says, okay, here we flip over, right? The one is on top, n is below. So it says that if n is 1, the answer is 1. Okay, if n is more than 1, then the answer is what? N times factorial of n minus 1, right? So here is the direct translation and code of the definition. Okay, next. You have this iterative factorial, which is this rule, right? Okay, last week the color was pink and now it's better. Okay, so product equals to product times counter, right? Okay, and then there's counter plus 1. James Ho, right? See? Okay, so very good. Those latecomers will help me remember your name. We'll play this called latecomer naming game. Okay? Correct, 1 for prof, 0 for student. Very good. Okay, so basically this is the translation, right? Okay? So you have defined factorial n. Okay? And, okay, iterative form, the way that you write iterative, this procedure in iterative form, basically you need to define some kind of inner helper procedure. So you can call it anything you want. Typically, it's some inner. What happens is that you define some inner helper procedure. Okay, this procedure will typically have this state variables. Okay, in this case, there are two state variables. There's the product, and there's the counter. Okay, and so the general form is that you define this inner helper procedure, and then what happens is that at the end you call the helper procedure with the variables. Okay, so this is the example. So essentially you go in there, we went through before. So let's look at this. This is the recursive one. Okay, and this iterative. Okay, so essentially if you look at it, okay, let's look at this one. This is this is Fibonacci. Okay, similarly, this is just a direct rewrite. Okay, using con instead of if, because there are more than 3 conditions. Right, and that's Aldrich Liu, right? Very good. Prof 2, student was 0. Okay, we are playing this game. This name is student game. If I succeed, then I win one. If not, then you all win. Okay, next. Okay, so this is the iterative form. Now, basically what happens is that you call the fib, okay, and you call the helper iterative procedure. Okay, here I didn't put inside. Actually, you can take this guy and put inside the fib n as the inner kind of procedure, right? So here what happens is that there are 3 state variables. There's A, B, and there's a counter. Okay? So what happens here is that the rule will be A plus B is A. Okay? A becomes B, and the counter you minus 1. Okay? So what happens in this case is that the counter is 0. When the counter is 0, you return B. Otherwise, you do what? You add the A to B, put it as A, and you let A be B, and then you decrement the counter. Okay? So this is the iterative form for Fibonacci. Okay, so let's take a look how this works. Okay, so first you call fib n. Okay, you call fib iter 1 n. So when fib 5 comes, okay, what happens is fib 5 will call fib iter what? 105. Alright, Then the next one, flip iter will call itself, right? Because counter is 5, but then counter is not 0, right? So you'll be flip iter, what? 1, 1, 4, right? Okay. Are we clear? After it will be what? 2, 1, 3. 3, 2, 2. 5, 3, 1. 8, 5, 0. And then what? 13, 8, minus 1. No, right? At this point, when you call flip iter, right? 8, 5, 0, right? What happens? You hit the base case, right? Where counter equals to 0. And this thing will happily return what? 8 or 5? 5, why? Return B, right? B is 5. And if you check, flip 5 is actually 5. Okay? Alright, so this is how you have iterative form. Notice that if you didn't do this, remember, if you didn't do this, you will have the recursive form, which is a what? What kind of recursion is? It's tree recursion, right? Remember, if you do the recursive form, you will be this dynamic tree thing, right? Okay? But now that you do iterative form, basically there's no padding operations because you see any clusters anywhere. Okay? You also see the same shape, no increase in space, right? Okay? So time proportional to n, right? Space proportional to constant, so it's order 1, simple. Okay, so that's good, very good. So now we talk about this space thing. So first of all, we want to, okay, so we have two things. What two things? Time and space, right, like physicists. So time will be how much the computation takes. Space will be how much memory it takes. Right, so, yep, that's what I just said. Okay, now, so two questions. So we need to ask, like, suppose factorial 5 is a certain amount of time. If I double it to factorial 10, how long will it take? Suppose 10 takes a certain amount of time. Suppose double it, how long will it take? Right, so you need to ask this question. How much more time? How much more space? Okay, this is the general idea in this thing called order of growth. And also, some order of growths are very nasty, so you know that if it's that bad, you cannot finish the operation. Okay, so let's take a look. So, you want to know whether it's like 2 times, 3 times, or the same. Okay, whatever. Okay, so there's some formal Palaf, right? Correct or not? Prof how many? Prof 3, yeah? Student 0, okay. So Prof wins. Okay, next. Alright, so like I said, you care about these two things, and there's a formal way of actually defining this, right? And you learn more about this in 3230, I think, or actually 2220 you learn more. See next class we learn more. Here it's very, very elementary. We are just going to introduce you some basic, simple concepts. So typically, if you have a resource, the resource is either time or space. You basically have a function to actually represent it, because you can figure out, for example, roughly it takes like 5n plus 6 steps, whatever. Okay, and the idea here is that you want to find a kind of a function called f of n. Okay, and if r is a resource that you need either time or space to do computation, you want to find the fn such that there's this thing called big theta of n of f of n. Okay, essentially the point now is that if you can find constants k1, k2, good morning Eileen, correct, right? So how many, Prof? Thank you. Okay. Alright, so basically if you can find two constants k1, k2 such that it bounds this r in between, right, for any sufficiently large value of n. Let me just show you. So suppose essentially as you increase the size of the problem, okay, there's r of n is a function of how much more time, how much more space it takes. Right. Now if you can find two constants and a function k, function fn, such that this amount taken is actually somewhere in the middle, then this is kind of sandwiched in between, then you know that this is the order of growth. Okay. The top line is called capital O of f of n, and then the bottom is this big omega. Okay. So it's actually this whole thing is called big theta. Okay. You learn more of this later, but for now we only concentrate on big O. Right, it means the upper bound. Right. So this is roughly the idea. So the question now is how fast does this operation grow in terms of time? Okay. Again, now it may seem kind of hazy, but then we will cover more examples in class. Okay. So intuitively, what does it mean? Intuitively, it means that if the size of the problem grows by doubles in size, then the resource required is increased to f of 2n. Okay. So basically, these are common functions for the amount for order of growth. There's a constant, which means that it doesn't grow. It means you don't care how big the problem is. It's always the same time or same space. F of n means it grows linearly. Okay, which means that if you increase by if you double the problem size, you will double the size as long or twice as space. Okay, obviously you have other things like n squared, n cubed, log n, and so on and so forth. Okay, the worst things are all the exponential things, which not worse, but they're pretty bad. Exponential will be very slow. Okay, so look at this example. This factorial 6, factorial of factor n. What is the order of growth in time? N, because it takes about roughly in this look at this, it's about 2n minus 1 steps, right? So you take about order n time. Space, how much space? Okay, how do you measure space in scheme? Okay, there are many ways of measuring it. This one also will be a bit sloppy, but roughly for us, we measure space using the number of deferred operations. Okay, so here you have roughly what? How many deferred operations? N minus 1, right? Roughly n minus 1 deferred operations. So the space will be order n, right? Okay, any questions? Yes, Samantha? No, this is not tree recursion. This is what recursion? This is linear recursion. Fib is tree recursion. Fib, Fibonacci. Okay, so linear. This would be iterative factorial. You will be order what? Time? Space? Order 1. Oops, typo. Okay, so it's supposed to be order 1. So this is just make sure that you know this is order 1. Oops, how do I type here? Okay. I said the right thing, but then somehow I typed the wrong thing. So amazing. Alright, so this shows that I'm a bit old already. So this one is to fix is order n linear time, order 1 constant space. Alright, suppose a computation takes 3n plus 1 steps. Okay, what is the order of growth? N. So essentially what happens is that you will throw away all the constants and all the smaller terms. Why do you do that? Because here we are looking at what you call asymptotic behavior, which means that the n is extremely large, right? When n is large, all the big term dominates, all the small terms drop out and are quite insignificant. Okay, so look for the biggest term. So how do you find the biggest term? You just have to see when n gets big, which one is the biggest thing, grows fastest. Okay, so take the largest term and drop the constant. Okay, how about this thing? 3n, what is it's order what? 3 to the n. Okay, so 3 to the n is the biggest term. Okay, so the basic thing is this: you identify what is known as the biggest is not the right word, it's the dominant term. Basically, when n grows large, it's the one that actually grows and dominates the whole time and space. Okay, and you ignore all this multiplicative and additive kind of constants. Okay, and note. Okay, log. You know that log a base b. No, log b base a is actually what? Log b, whatever base divided by log a or whatever base, right? So to some extent, log doesn't matter. The base doesn't matter because frankly the base is just a constant. Okay, so log is just log. Okay, next. You will do more stuff, I think, in even 12220 also. 123, 1220. Basically, this is a lot of stuff. Okay, right now, we just introduce you to these ideas, okay, and you'll be taught more about this sort of growth in the future. Okay, so for now it's very simple. For now, what we need to do is that you need to be able to count, okay, just two things. Count the number of computations, basic steps required to finish computation, okay, and the other thing you count is how many pending operations. That's all. Okay, for this class, it's really quite basic. Right, and the first thing you need to do is to identify which are the basic computations. Okay, and then if you want to do this thing, analyze a certain procedure. Okay, you just try a few try out okay, for like write out something for small values of n. Okay, and then you extrapolate and try to find a pattern. Okay, and look for this worst case scenarios. Morning, who you guys are? Alex, next lecture. A bit early, right? I'm not popular. They come next lecture, in my lecture. Okay, anyway, this one is a quick table showing you how the terms will grow. Basically, exponential is really bad. Okay, basically h universe is 2 to the 5, 2 to the power of 29. For 2 to the n, very fast, the thing explodes already, right? So basically, anything that is, exponential is very hard to finish computing, okay, for large numbers. Okay, so the key thing to understand from today's lecture is this, okay, that different ways of doing the same computation can actually consume drastically or dramatically different amounts of resources, both time or space, okay? And this is something you need to pay attention to, not here, okay? In 11s, the objective is not so much to be efficient or to optimize. The objective is just to solve problems, okay? And to understand how to solve problems. Next semester, when you take 2020, this is when you work on these things called efficiency and other things. Okay, so now that we have kind of covered this simple topic on, okay, it's relatively simple in 11s on order of growth. You now revisit recursion, okay, by looking at examples. Okay, recall recursion has got two basic things. First, you solve the problem for a simple base case, okay, that you can just look at eyeball and see and spot out the answer. And then you need to express or divide a problem into one or more smaller problems of the same type. Okay, this is very similar. Who knows this? Mathematical induction. You don't know? Who's behind? You don't know, right? Okay. Good. So hopefully you all understand this. Okay, so let's look at the analogy. Induction, you do what? You start a base case, right? Correct? Prove that, don't know what, B, something is right. Then you say that assume K is okay. Prove that K plus 1 okay, right? Alright, this is what you do in induction. Alright, then you must always work for any case greater or equal to B, right? Because the idea is that you start from B, you build up. Correct? Recursion is quite similar. Recursion essentially, first you derive a problem you express a problem of size n in terms of problems of size smaller than n. Okay? And then after that, again, you figure out there's some base cases or base cases that work. Alright? And then essentially the procedure can compute. Okay? Now, the thing to understand is this. Sometimes you may need to use more than one base case. That means sometimes you just want n equals 0 is enough, n equals 1 is enough. Sometimes you need multiple base cases. When is this? Why? Okay? You can answer this inside your IBLE forum. Okay. Other times you may have to express the problem in terms of another form, and that form will also express it back in the same form. This will be these kinds of things called mutual recursion. And in certain things like sine, cosine, this is very natural. Okay, so it's very natural to express sine in terms of cosine and cosine in terms of sine. It's very hard it's much more complicated to express sine in terms of sine. Okay, so sometimes it's just a more natural way of doing it. So these are the kind of general ideas. Okay, so first example we're going to talk about is this thing called Euclid's algorithm. Okay, who knows this algorithm? Wow, okay, it's okay if you don't know. But algorithm is the following. The algorithm is for finding this thing called the GCD, which is the greatest common divisor. So given two integers, you want to figure out what is the largest integer that will divide both of them. Okay? And it turns out that this thing will work. Okay, you can prove this obviously mathematically, but I really don't care how to prove. Just assume that Euclid was a smart man and he figured it out and it's right. Okay? Then essentially what you say is the following. The GCD of two numbers A and B, okay, is the GCD of B, the small number, okay, and R, which is the remainder of A divided by B. Okay? And basically you keep doing this. At some point, your R will be 0. Because the point now is that R is obviously smaller than A and B. It has to be the way, because R is the remainder, right? So basically, you take the smaller number, you put it in front, and then after that you can generate a number that is smaller than the smaller number. So obviously the right side keeps getting smaller and smaller. Okay, at some point you will get to a point whereby there's A and 0. Okay, and A will be your answer. Okay, so that's just how the algorithm works. Okay, so the right this one, the line is off. Okay, I don't know why. I think it's a version of like a PowerPoint. Okay, now so the idea here is that if GCD AB equals to this thing, then this is true. Okay, so the first thing you do is GCD A or B. Alright, what's the first step? Will be the base case, right, which is what? If B is 0, return A, no brainer. If B is 0, return A. Okay, this again, no brainer one. The algorithm is on the right. Your whole goal now is do translation from the algorithm to the code. Completely trivial. Now, if B is, if B is not 0, then what to do? You return GCD of B and remainder AB. Okay? And how come I don't care whether B is small or B is bigger? Do I care? No, I just don't care. Okay? In this case, you just sort the thing, so it makes no difference. Okay? You think about this now. I don't really care. Okay? But after a while, the smaller one will move to the left. Okay? But think about this. But this is all it is. So example, suppose your GCD 20640. That means you will move 40 to the front. 6 will be the remainder of 206 divided by 40. Right? Now that 46 on the left. 46 is what? The 6 moves to the left. You divide 40 by 6. Remainder is 4. Right? Move 4 to the left. Divide 6 by 4. Answer is 2. Right? Do the same thing. You get 2, 0. So you know that the GCD, the greatest common divisor of 206 and 40 is 2. Yes? Okay lah. Think about it lah. Okay? Anyway, that's the question I asked you, right? Must you put the larger number first? Okay, so you think about this and you can post on the forum again if you want to. Okay, so this is the answer. All get it? Simple enough, Okay, the illustration here is this, You're not required to prove the algorithm, but if those of you who are the double degree manager, double degree, DDP 1, DDP 2, 3, 4, 5, DDP, no you're not, you're the CEG. DDP 1, 2, 3, 4, I find you go and prove for the math side why this is true for kicks. Sorry? Yeah, correct. You stop it, okay? So it's cool, right? Interesting, Alright, so next one. How's Hanoi? Yes? The proof of why this is correct. Oh, math major, right? Cannot do, switch to comp science, drop math. It's okay, one. We will take you. We are very kind, okay? We will take, if you cannot do math. Okay, next, we have Taos Hanoi, Okay, you all saw this as an example before, I think. So the general idea here is to move all this from this side to that side. Okay? And the rule here is what? The rule is that you cannot do what? You cannot put the bigger one on top of the smaller one, right? Very simple. You all play during primary school or whatever. Go to science center, you can find. Okay? So this is good. So you want to do this, move here. Okay. Recursion. So what do you do? The first thing you do is what? Two things in recursion, right? First thing will be base case. What is the base case? Not everything on target lah. First base case is, okay, simple base case is, and then, okay, first off base case, second you divide into small problems. Base case, so what happens is know this. Basically know this means nothing to do lah. Okay, return good already. Okay. Suppose if you know how to move 3 disks from A to B, it means you know how to do it. If you know how to move 3 disks from A to C, okay, then the claim is that I can move 3 disks from A to B. Why? Because I just pretend that that B is C and C is B, right? Then whatever I used to do, I just, instead of moving to B, I do C and so forth. So I can definitely use the same steps to move from A to B. Alright? All follow? Okay, good. Now, then how you do for this? You will do what you did last time to move 3 disks, from A to B, right? And then you will do what? You move the last disk over to C, okay? And you move everything from B to C. So this is the idea. So if you express this procedure in terms of a procedure, move tower, size from extra. So size is the number of disks. Alright? And from to and extra are the 3 packs that you see. Okay, so what's the base case? Okay, if there's no disk, you say happy already, done. Right. Now if they are otherwise, you do what? You move the, who is this, sir? Who are you? Next class. I must be really popular, man. Half an hour before next class, come and see my class. Okay, come, sit down. Alright, so, for more than node this, what you do? You move tower from to extra using 2 as the extra, right? And how many disks you move? You move at size minus 1 disk, correct? Okay? Then you do what? You move the last disk from to 2, right? Okay? And the last step is what? You move the n minus 1 disk from the extra to the 2. Okay, notice essentially I'm just swapping the arguments, right? Because the first procedure, the original procedure moved from the from to the to using extra. Then if you start moving these things around, you actually do the slightly different things. Okay? Now, what is this print move? Print move is very simple. Print move is just this. Okay, you all haven't learned this before, but print move is just display new line, then you move something, pop this from here to here. That's all. It's just a printing statement. Okay? So essentially, I can quickly show you this. Hopefully it works. Alright, so this is the code. I mean, I will also upload some code from the lectures online, so you can take a look and try. Hey, so slow. Okay. I stopped. Okay, now this thing loads, I will do something else. Okay. So, question. What is this compute? Compute full, right? Say again? B to the power of E. Okay, maybe. We'll see soon. Okay, so this is the power of Hanoi. So you have the code. Okay, very simple. Only like 12 lines. Okay. Then if you do move power, how many you want to move? 9,000. You can wait till tomorrow. Okay, let's just do a simple one first. 3. Okay. So simple is from. Okay, 1, 3, 2. Okay, basically I'm calling the first tag, I call it 1. The last tag, I call it 3. The extra, I call it 2. Okay, so I press enter. You cough out. Basically, move top this from 1 to 3, move 1 from 2, and whatever so forth. Okay, so if you do the simple one here, another one. Let's say 3 is too little. Let's try 6. Okay, and then you print out for you. You're very free. You can verify. Correct. Okay, but this one shows you they can done quite quickly. Okay, this is B to the E, right? Okay, take a look. Basically, this is this. Except what I did was that I went to do what? I replaced foo bar with something that's more meaningful. Okay, so moral story also is please don't call the thing foo bar. Thank you very much. Okay. So what this thing does is actually what kind of procedure is this? Is this iterative or recursive? Iterative. Why? Because it defines an inner helper procedure, okay, and then it doesn't have any deferred operations, and it's actually using the state variable to compute. So it computes A times B to the E. Okay. Sorry, the power product computes A times B to the E, and what I did here is that I put in 1 BE, so A is 1, and so the answer is B to the E. So this thing computes exponentiation, the base to the power of E. How long does this take? What are you doing here? You are multiplying B by B n times, right? The total time taken will be linear, right? Are we clear? Okay, linear. Space. This is the iterative. Essentially, you see power product, one straight line is all the same size. Okay, linear. Okay, can we do better? Only Richard thinks we can do better. The rest of you think can do better. Yes. Of course can. That's why we're in this lecture, right? Okay, so the idea is the following. Okay, so now you look at this. Obviously, this is true. Right? This is not magic. Right? This is math, right? We know that if exponent is 0, answer is 1, right? You all know that, right? All know. And if you don't know, I'll send you back to primary school. All know. Okay, so after that, you have two other possibilities. One is that B is even. The other one is that B is odd. Right? It turns out that if B is odd, then you have this simple thing which is B to the E is just B times B to the E minus 1, right? Okay. if b is even, you can take the exponent and halve it, right? And then if you do b squared to the power of e over 2, you have the same thing back. So essentially the left and right side are the same. Has to be the case because this is equality. Are we all clear? So this is very simple, right? So we do this. And if you look at this thing, this is exactly a con statement, right? If you have a con, okay, if e is 1, sorry, so if e is, if e is 0, then the answer is 1, which is what we said earlier, right? Now, if e is even, we call what? We call this fast tip, whereby you square the b and you halve the e, right? This is exactly, okay, so I say again, the second line here is exactly the second line here, no magic, okay? And the last line, b multiplied by fast tip, this thing, is exactly this thing, okay? I'm just literally translating this algorithm. Actually, it's not an algorithm, it's just a definition, mathematical definition into code, okay? How fast is this? It depends on what? Input, but on the whole is log of e, right? Okay, so this thing is faster. The earlier one will be order of e, order n, okay? Linear, this will be log. Okay? Space requirement? So this one is actually space requirement also log e, because this is actually recursive. Okay? Good question. We will discuss it in class, but for now, eyeball this thing and try to figure out yourself. Okay, we'll discuss more carefully in class, exactly how you do this. Essentially, you need to go and count the steps. Okay? Now, so the question is, can we do this iteratively? Answer is yes, okay? So this is the way to do it iteratively. Okay, but I will just flash through this so that you all can go back and try it yourself. Okay? Okay, so the answer, but go back. So essentially, you should do this. You should go home, okay? Try to write these things the first way, and try for practice to convert into iterative form. This is for practice. Okay, now we do the last nasty thing. This is very nasty, super nasty. Okay, so y'all must stay with me. Okay, all focus very hard. The math majors focus harder. It's all matrices. Okay, so first of all, consider the following expression. X0, Y0 is AB. Simple. Right. Now let me define the following. Suppose I define x of n, y of n, okay, to be p x of n minus 1 plus q of y n minus 1, okay. At the bottom will be r x of n minus 1 and s y of n minus 1. So suppose I'm saying that, it's actually saying that xn is this thing, is actually the product, xn is the sum of the previous x and y multiplied by some constant, p and q. Similarly, y is the yn, so think of x and y as a sequence of terms. Y of n is actually similarly a sum of the previous two constants, the previous two terms multiplied by some constant. It turns out this form over here, this one can be obviously expressed in matrix form, which is PQ, RS, and so forth, right? The business economist, okay? Business lady, okay, right? You have to do this as well, okay? Good. Okay, so this is so far okay? All clear? Okay, very good. Now, obviously this is true, right? Now, if you can express this thing in terms of this thing, it's quite clear to you that xn minus 1, yn minus 1 is what? It's actually PQRS multiplied by xn minus 2 and yn minus 2, right? So in other words, it's actually quite clear that this is true, right? It's quite clear that xn, yn is actually PQRS to the power n multiplied by the AB, right? Because AB will be the first, what's that? AB is 0, right? x0, y0. Okay? Okay, here, no magic. There's no magic here at all. Okay? This one, basically, I'm just telling you some simple matrix definitions. Okay, now, suppose that is true. It is true. I mean, it's not suppose, it is true, right? Then, obviously, xn and yn can be written in this form, right? When n is 0, you know that it's AB, right? I just told you that. Okay? Now, and in general, because xn and yn is this PQRS thing, you of course can do this, right? Because the bottom here is exactly the same as what you saw in the previous example. except that now it's nastier. I mean, it's the same thing. Now it's a matrix instead of a P and a Q. Instead of a simple, like, B or something. But it is the same exact form. Any questions? Are we clear? Anybody doesn't agree with this? Who agrees with this? Agree. Agree. Jerome. Okay, let me make sure we're on the same page. Chen, right? Agree or not? Yeah, it's the same. I mean, basically you do multiply this thing together, this thing you have obviously what, n, right? You multiply this and this, obviously it's n, right? It's the same. This is a mathematical equality, there's no difference. Except that when n is even, you know that n can divide by 2 and you still get an integer. When n is odd, you cannot. Okay, so you all agree this definition is correct, right? And it's simple to understand. Okay, good. So after this explanation, now for kicks, let's assume that this function a, b, r, n equals this. Okay. Just say this. Let's say this is true, because you know that this thing. See, this thing is this thing, right? Correct. This thing is this thing, correct. So this thing must be this thing, right? But this thing is actually you can think of it as a function of how many variables? 7 variables, right? Because there are like P, Q, R, S, A, B, and N are 7 things, right? So you can say that, suppose I say this thing is this thing, then because this thing is this thing, then this thing must be this thing, correct? Again, nothing new, it's all the same, right? Everything's the same, very simple. Now, then obviously, if you look at this thing, okay, you can go and multiply this thing together, right? P, Q, R, S, Q, R, S, you can multiply this thing, you will have this thing, correct? Okay, so this thing is exactly the same as the previous thing, except that what I've done is over here I've multiplied in the square matrix, the P, Q, R, S, Q, R, S as square. I've multiplied and becomes this thing. Okay, this is the same as this thing here, right? Okay, now this thing has P, Q, R, S multiplied by AB, right? Obviously, I can go and multiply it to give you this thing. Alright, so you all agree with me that this page is exactly the same as the previous page. No difference, right? Very cool, no difference. Now, okay, but you know that the left side is this thing called F, A, B, C, D, whatever, right? Okay, again, I say this, you know that the left side is actually an expression consisting of 7 variables, right? N, A, B, P, Q, R, S. So the left side, I can express it in terms of this thing. Agree? Agree, right? Okay, now, then you also know that this thing is similar in form to this thing, right? Except that the P is now P squared plus QR. Oops. Q is now P plus SQ. N is N over 2. Okay? So basically this thing, I can re-express in this form, right? Correct, right? Because the same thing, right? I mean, I define F, A, B, C, D, whatever as the PQRS thing, right? Now that PQRS has changed, then all I need to do is replace the PQRS with this thing, right? You agree? Right. Now, similarly, this thing here is the same as PQRS, except that this is AB, right? Last time it was A and B. So AB ends up to be here, A and B, but A and B are not A and B. A and B is this rubbish thing. And then the PQRS remains the same. Okay? PQRS is the same thing, but the exponent is now n minus 1. Okay, so you all agree with me that the left side, right side, these are equivalent again, because I've done nothing. I've just done some transformations. Call this thing, that thing, done this, right? Okay? Now, so this is kind of cool. Then suppose I tell you this. What I tell you this? Suppose I tell you that F, you know that F of A, B, C, whatever, is actually a pair, right? Upstairs, downstairs. Okay? Suppose I tell you that, I don't care about the top part. Sorry. I don't care about the bottom part. I only care about the top part. Then the top part I call it G of N. G of N, A, B, P, Q, R, S. Then it's quite true that this must be true, right? Because suppose that F, N, A, B, P, Q, R, S is G of this thing, and something at the bottom, I don't know what, maybe H of whatever. But I don't care. Then it's quite clear that the top part and bottom part must have the same relation, right? Okay? Are we clear? Okay, so far I've done nothing special. I've just taken some mathematical expression, I've just simply transformed it into another form. Okay. Now with this thing, it turns out that the following is true. Now, if I use A is 0, B is 1, P is 0, Q is 1, R is 1, S is 1, then x of n is equal to flip of n. Fibonacci means x of n will be the Fibonacci number of n. Okay, because you look at it, you're doing that exactly. So basically, because if I let A be 0, B is 1, this will be true. Okay, and then you look at this relationship. It means that if P is 0, Q is 1, R is 1, S is 1, you get this. Okay, what you will find is that essentially you will generate x of n generates the Fibonacci series. Okay, now with that, what you can do is you can write this thing called fast Fibonacci, which means that you can actually do Fibonacci in how fast? Logarithmic time. Okay, so basically with this particular procedure, you compute Fibonacci in logarithmic time. Okay. So orders of growth, recursive fib will be time is what? Exponential. Space will be linear. Iterative time is linear. Space is constant. Fast fib, log and space will be okay. So this is how you can change this. Okay, why? Okay, this is why, right? Good question. So don't think about it and explain. Okay. So summary, I'm about done. Okay. So the time and space requirements are important. Okay, different ways of computing can give you different times. Okay. And then recursion simply has two ideas. Recursion. First idea is that you must figure out base case. Second idea is to figure out how to divide the problem into small problems. Okay. And the last thing is this fast fib technique, which essentially means that you need to go and halve the index. Okay, so that you get faster. Okay. Okay. Two things to think about at home. Okay. How would you write a procedure? Okay, which will compute sum of digits. Okay, given an arbitrary positive number, sum of digits. Okay. Now after that, you want to write another recursive procedure that will, instead of returning the sum of digits, you return to you the product of all the digits. Okay. How do you do that? Okay. Now the general idea is this. What's the pattern you see? Suppose subsequently you want to write a procedure that actually gives you the sum of the squares of the digits. How we do it? Okay. So this is what you want to think about this weekend. Okay. So why is it cool? Because you can ask your friends now. How many of them have learned how to solve this problem? Okay. 1010. I don't think they are anywhere close to what we're doing now. So it's kind of we're accelerating. Okay. And hopefully this works. Okay. So now I will do. Okay. Those of you who need to go, please go. Those of you who are around, you can look at your scheduling problems. Okay. So this is the. Alright, so this is a list of all the DGs. Those of you who have trouble, come and talk to me.